Welcome back to the Deep Dive. Today, we are moving far beyond the passenger vehicle market and strapping into something heavy, highly specialized, and absolutely vital to the future of infrastructure.
We really are. We're looking at the electrification of heavy-duty vocational vehicles.
Forget the shiny sports cars and the commuter sedans for a moment. We are deep diving into the blueprint for the 400-volt P2 hybrid plus ePTO cement mixer truck.
Yeah, and this is a deep dive into serious operational engineering. The source material we're looking at isn't, a standard industry news brief. It's a high-level definitive consultancy report.
And what's it for?
Well, it's designed to address a fundamental challenge.
Yeah.
How do you transition these traditional diesel-minded engineering teams into highly specialized electrical system engineering?
That transition is the key context here. The goal of this report and our mission today is to crack open this blueprint and extract the key strategic and technical decisions, the ones needed to design a reliable, safe, and economical high-voltage system from the ground up.
Right. We're essentially walking through the process that helps an OEM develop the capability to execute a complete high-voltage system architecture development plan from scratch.
And the stakes couldn't be higher.
Not at all. The foundational value proposition highlighted right up front is it's critical. If you miss key architectural steps, you invite just astronomical rework costs down the line.
I can imagine.
So we have to understand how this design meets these incredibly stringent international requirements. ISO 26262 for functional safety, ISO 64693 for electrical safety, and ECE R100.03 for overall vehicle certification.
And these are really the non-negotiable pillars of entry into the modern heavy-duty market.
Exactly. These regulatory acronyms, they aren't just paperwork. They are the architectural guardrails.
So they determine not just if the vehicle works, but if it's legally and fundamentally safe to operate in the harshest environments.
Precisely.
Okay, let's unpack this blueprint, starting with what sounds like the biggest strategic choice they had to make, the specific powertrain topology and the voltage platform.
Right. So the first pillar of this architecture defines the powertrain, and the source material makes a very strong, I would say nearly mandatory case for the P2 parallel hybrid architecture.
Okay, let's unpack this. So P2 means the electric motor is physically placed between the engine and the transmission, connected via a separation clutch, K0. But why is this specific arrangement basically mandatory for a cement mixer truck? Their duty cycle is notoriously demanding. It's nothing like a standard semi-truck.
The P2 choice is entirely dictated by that unique and frankly brutal vocational duty cycle of a mixer truck. A standard logistics truck is optimized for continuous highway speed.
Right, steady state.
A cement mixer truck, however, it operates with high load starts, long periods of low-speed maneuvering and idling, and the continuous, non-negotiable need for drum rotation. The P2 architecture, it solves all of these problems at once.
Okay, so let's start with the launch phase. I know heavy-duty vehicle starting power is a major mechanical weak point, especially on construction sites.
It's a massive mechanical challenge. I mean, we're talking about vehicles often exceeding 32 tons gross vehicle weight needing to start repeatedly on steep construction site grades, potentially 30% grades. Wow. Traditional calculations and dynamic simulations show this demands wheel torque up around 91,000 Newton meters.
That's huge.
It is. And if you rely solely on the diesel engine clutch, you burn through consumables incredibly quickly.
And the P2 motor solves that because of its immediate torque delivery characteristics.
Precisely. The P2 motor provides its peak torque at, 0 RPM instantly. This burst of immediate electric torque is blended with the diesel engine's output right at the start.
So it's not just a performance boost.
It's a massive performance boost, but more importantly, it drastically reduces the required friction and slip from the physical clutch. It minimizes wear and extends the maintenance interval for a critical, very high-cost component. It is a maintenance saver enabled by electrical performance.
That's compelling, a performance enhancement that actually pays for itself through reduced maintenance costs. What about when the truck arrives at the site and begins its, slow, continuous operation?
Right. That brings us to the second key advantage: zero emission and quiet operation, the ZEV mode.
Okay.
With that K0 separation clutch open, the engine can be completely turned off. The P2 motor then provides pure electric, low-speed crawling for maneuvering on the site, which is often mandatory in noise-sensitive zones.
And crucially for the drum, right?
Crucially, yes. It provides continuous, quiet drum rotation during unloading. This is vital for residential neighborhoods or designated zero-emission zones, and it allows the truck to operate 24/7 if needed.
So it facilitates urban logistics compliance while also enabling quiet operation. We mentioned continuous operation. What about efficiency and energy recovery? That's another huge challenge for stop-start city driving.
And P2 shines here. It's because of its placement before the transmission. Mixer trucks operating in urban and construction environments have frequent stop-start cycles. They brake often.
All the time.
So, since the e-motor is mounted before the gearbox, any kinetic energy recovered during regenerative braking is mechanically amplified by the transmission's multi-stage reduction ratio.
So it's a multiplier effect.
It's a multiplication factor. It means the system maximizes the energy captured during every single braking event, which substantially boosts the overall fuel economy and the range of the battery.
So the P2 choice isn't just about fitting a motor somewhere. It's really dictated by a rigorous analysis of torque requirements, emission zones, and mechanical advantage.
It is. It's the most optimized solution for this specific duty cycle. And now, within the P2 model, the report mandates a further technical constraint: off-axis integration.
Off-axis.
This is a purely mechanical decision, but it has huge electrical implications.
Okay, why the need for a specific physical layout like off-axis? What stops them from just bolting the motor in line with the crankshaft?
It all comes down to physical space. The chassis of a cement mixer truck is incredibly space constrained. You have a long wheelbase for stability, the massive rotating drum volume, and often complex air and hydraulic systems all crammed in there.
So a coaxial design just doesn't fit.
A coaxial P2 design adds way too much axial length to the drivetrain.
And pushing the transmission back causes all sorts of mechanical friction problems elsewhere, right?
Exactly. Pushing the transmission back forces higher angles on the universal joints, the U-joints in the drive shaft. And if you exceed the recommended U-joint angles, you get vibration, increased stress, and premature failure.
So the off-axis solution.
The off-axis solution mandates the motor be installed parallel to the drive line, connected via gears or a chain drive, which effectively minimizes that extra axial length.
That axial length control solves a critical longevity issue. What other engineering benefits does the off-axis design unlock for the OEM?
Two major things, and both of them support the consultancy's mission of, building platform capability. First is modularity. Because the motor assembly is external, you can easily swap in different power levels, say moving from a 120 kilowatt unit for lighter loads up to a 220 kilowatt unit for heavy off-road use. And you can do this all without altering the fundamental engine gearbox bell housing interface.
So that allows for rapid platform development across an OEM's entire heavy-duty lineup using common interfaces.
Right. Platform commonality translates directly into lower manufacturing and inventory costs.
And the second benefit?
The second benefit is optimized thermal management. The parallel placement of the off-axis motor makes it much easier to integrate a dedicated water ethylene glycol or WG cooling system.
And that's non-negotiable.
Completely non-negotiable. The ePTO function requires sustained high-load operation, especially when you're mixing in hot weather. Effective, dedicated cooling ensures the motor's longevity and prevents thermal derating.
Got it.
And as a final crucial detail, the K0 separation clutch must be a wet multiplate design, and it has to incorporate a torsional damper to handle those frequent electric-to-engine handoffs smoothly.
So the off-axis design is a really elegant engineering solution to a harsh packaging constraint. That brings us to the second major strategic pillar, the voltage choice. We are looking at a 400V platform. So nominal 400V DC, operational 280V to 450V. In the broader EV world, 800V is touted for its charging speed advantages. Why is 400V the mandated choice for this vocational workhorse?
This is a classic case of prioritizing utility, cost, and reliability over raw speed. The report strongly advocates for 400V because the decision metrics are weighted so heavily toward commercial viability in a specific harsh environment.
Okay, let's start with cost. How significant is the difference?
The first metric is cost and supply chain maturity. 400V commercial components, the inverters, the DC-DC converters, even the high voltage harnesses are mature, they're industrialized, and they're available at high volume.
So they're off the shelf, basically.
Pretty much. The report estimates this maturity offers a significant 20–30% cost advantage over developing or sourcing 800V systems, which are still scaling up outside of, specialized luxury or passenger vehicles.
But hold on. 800V allows for smaller, lighter cabling because you transmit the same power at half the current. Weight is critical for a truck. How do they justify the trade-off of potentially heavier 400V cabling against that 20–30% component cost saving?
That's an excellent point, and the calculation for heavy duty is different. While 800V does use thinner cables, the cost of that thin cable is offset by the complexity and high cost of 800V power electronics, especially the semiconductors.
I see.
For a mixer truck, the weight savings from thinner wires are secondary to the massive upfront cost saving on the PDU and the inverter itself. The financial advantage of 400V component commonality it simply outweighs the marginal cable weight reduction in this segment.
Understood. Cost rules in the commercial space. What about charging?
Well, the second metric is charging compatibility. Mixer trucks primarily use depot charging at the fleet's central yard. Existing industrial infrastructure, including older charging stations, natively supports 400V platforms.
So no new infrastructure needed.
Exactly. If they adopted 800V, every single truck would require a complex, costly boost converter on board just to use standard depot charging. And that adds weight, complexity, and another point of failure. Sticking to 400V simplifies the entire fleet ecosystem.
And complexity is definitely the enemy of reliability in a vehicle that faces constant vibration and stress. So what is the final decision metric, the one relating to the environment?
Safety and reliability in harsh environments. Construction sites are hostile, they're dusty, wet, often muddy, and they're subject to high-pressure washdowns.
Right.
800V systems require much greater physical separation between conductors, what we call creepage and clearance distance, to prevent arcing and insulation breakdown. At 400V, the requirements are less stringent, which inherently boost the long-term reliability of the PDU, the bus bars, and the high-voltage connectors when they're constantly exposed to humidity and pollution.
So 400V is the pragmatic, reliable, and cost-effective choice. It perfectly balances performance with the harsh reality of the construction site and the economics of fleet operation.
It really does.
Okay, so having established the P2 off-axis topology and the 400V platform, let's drill down into the component-level engineering definition, the specialized heart of this system.
Right, so we move now to the detailed technical definition of the high-voltage system architecture. This is where the transition from diesel thinking to electrical thinking becomes, concrete.
Literally. So this starts with the topology overview, mapping the truck's high-voltage nervous system.
The core principle here is the centralized 400V DC link architecture, where the HV battery, the ESS, is mandated as the single energy source. Power is then distributed radially from this central source to all the loads through the High Voltage Power Distribution Unit, or PDU.
That PDU is the critical hub then. It must follow some very strict rules for safety and distribution.
Oh, absolutely. The blueprint mandates 4 non-negotiable design principles. First, the single energy source approach, which simplifies energy management and control algorithms. Second, centralized distribution, which requires zoning loads into drive, auxiliary, and body.
So P2 motor, e-compressor, ePTO.
Exactly. Third, the HVIL, the high voltage interlock loop, must cover the full circuit and cannot, under any circumstances, be bypassed.
That last point on HVIL is paramount for safety.
It is absolutely non-negotiable. And fourth, the pre-charge and main discharge paths must be physically independent to prevent a single-point failure from compromising the system's ability to power up or safely shut down.
Okay, let's look at the ESS itself, the battery unit. What are the requirements for power storage in a vehicle that's subject to such extreme vibration and heat cycles?
Well, for battery chemistry, the priority is LFP lithium iron phosphate. This is specifically chosen over, say, high energy density chemistries because LFP offers superior thermal stability and cycle life. And those are non-negotiable for heavy engineering vehicles that operate for 12-hour shifts and have really demanding charge and discharge profiles.
And given the conditions, environmental protection must be extreme. The battery is constantly getting hit with mud, dust, and pressure washing.
It has to be military-grade protection. The requirement is an IP67 rating for the battery pack enclosure itself, meaning total protection against dust and temporary immersion. But the critical detail is the connectors. The HV connectors have to meet IP6K9K.
What does that extra K9K suffix imply in the real world?
It means it must withstand high-pressure, high-temperature washdowns. So if the driver needs to clean the chassis after a shift on a muddy site, the connectors have to be guaranteed not to fail when they're hit directly by a power washer nozzle. This dramatically increases the component robustness requirement.
That's a serious operational constraint driving component selection. Now, the battery management system, the BMS, you mentioned an ASIL D target. That's the highest safety standard. Why is ASIL D recommended for the BMS?
It's recommended because the consequence of BMS failure is thermal runaway, which is catastrophic.
Yeah.
To achieve ASIL D, which is the standard usually applied to mission-critical systems like brakes, the system must have an extremely low probability of random hardware failure and very high diagnostic coverage.
So how is that achieved?
The report recommends a master-slave architecture. The master BMS handles the critical, high-level, safety-critical functions: state of charge, state of health, setting percents power limits, controlling the main contactors, and continuously monitoring the HVIL.
And the slaves.
The slave CMU cell monitoring units are distributed. They handle the granular voltage and temperature measurement, typically one module for every 12 to 16 cells.
And the communication between them, it has to be robust.
It must be isolated. Communication within the BMS uses a dedicated isolated CAN bus running at 500 kilobits per second, and it's completely separate from the main vehicle network. This segmentation ensures that an internal BMS fault cannot compromise the vehicle's communication network, and vice versa. It's a key requirement for high ASIL ratings.
That dedication to safety starts right there at the cell level. Now let's move back to the PDU. If this is the heart of the power distribution, the internal design must be optimized to handle massive current without creating electrical havoc.
Absolutely, and this is where the engineering detail demands the elimination of traditional methods. The source strictly prohibits traditional cable jumping inside the PDU.
No cables inside the box.
No, instead the mandate is for laminated bus bars.
Okay, why is traditional wiring now deemed unsafe or inadequate inside the PDU for this application?
It's a matter of suppressing electromagnetic noise and protecting the power semiconductors. Traditional wires have higher self-inductance. If you imagine electricity flowing through a kinked garden hose, that's sort of what inductance is.
Right.
When the IGBT or silicon carbide switches in the inverters turn on and off rapidly, hundreds of times a second, that stray inductance causes massive destructive voltage spikes.
So stray inductance is like electrical turbulence.
It is precisely electrical turbulence. Laminated bus bars, which are hot-pressed layers of copper conductor and thin-sheet insulation, create a nearly perfect, smooth channel. This construction significantly reduces stray inductance, effectively eliminating those voltage spikes and protecting the highly expensive semiconductors in the inverters from premature failure.
That's a design choice that directly counters a fundamental physics problem in power electronics. What are the material requirements for these bus bars?
They must use C11,000 ETP copper with full nickel plating.
Why nickel plating?
Because, as we discussed, these vehicles operate in high humidity, polluted environments. Nickel plating prevents the copper from oxidizing. Oxidation increases resistance, and increased resistance leads to heat, which causes expansion and contraction. And eventually, you get loose, unstable contact resistance, which compromises safety.
So the nickel is a mandate for stable long-term contact resistance in the face of moisture and heat. What about the thermal limits for the bus bars themselves?
The current handling capacity is strictly defined. Bus bars must handle a continuous current capacity greater than or equal to 1.3 times the maximum working current. More importantly, thermal rise simulation has to ensure the temperature increase, the delta T, is no more than 40 degrees Celsius.
40 degrees Celsius seems like a very specific, strict limitation. Why not allow for, say, 60 or 70 degrees?
That limit is tied directly to the longevity of the adjacent components. High temperatures accelerate the degradation of insulation materials, contact surface plating, and surrounding connectors. By capping the thermal rise at 40 degrees, significantly below the material limits, you drastically reduce thermal cycling stress and ensure that the PDU maintains its functional safety rating, ASIL B or C typically, throughout the vehicle's projected 10-year lifespan.
It's a design choice for robustness, not just performance.
Exactly. And the contactors themselves, the safety cutoff switches, they must have load breaking capability. This means they can safely interrupt current while the system is running at full power. They also need a fail-safe disconnect time of less than 20 milliseconds.
Wow, that's fast.
That speed ensures if a safety fault is detected, the massive energy flow is shut down almost instantaneously.
And the PDU is feeding everything from there.
Everything. The P2 drive inverter, the ePTO mixer inverter, the e-compressor, the DC-DC converter, and the electric hydraulic power steering.
Finally, let's look at the inverters and their critical voltage management component, the DC-link capacitors.
The selection here is absolutely critical for reliability during frequent regeneration events. The mandate is for metallized polypropylene film capacitors, or film caps. not traditional electrolytic capacitors.
Why not electrolytic?
Film caps possess self-healing properties. If a microfault occurs, the metallization around it vaporizes, which clears the fault without a catastrophic failure.
That self-healing feature must be key in a high-vibration environment.
Absolutely. They also boast a lower equivalent series resistance, or ESR, typically less than 1.5 milliamps, and a much higher ripple current capacity. Electrolytic capacitors would just heat up and fail rapidly under the frequent high current pulses generated during regenerative braking in a start-start cycle.
And what safety margin is built into the voltage rating?
It has to be significant. The rated voltage of the capacitor must be at least 1.2 times the system's maximum operating voltage. So if the system maxes out at 450 V, the capacitor must be rated over 540 V.
Why so much headroom?
That extra margin is critical because during an aggressive regeneration event, especially at a high state of charge, the battery voltage can spike. This margin ensures the component safely absorbs those transient voltage surges, protecting the entire high-voltage bus.
This detailed component analysis really underscores the systemic approach. Every part is chosen not just for its function, but for its resilience against the unique duty cycle and physics challenges of the application.
The architectural decisions here directly lead to long-term operational reliability, which is the cornerstone of the consultancy report. So now we can shift to the system's most unique challenge, the operational hazard that necessitates extreme redundancy.
This is where the truck's purpose really defines the engineering. Let's review the ePTO architecture first, the electric power takeoff that drives the mixing drum.
The ePTO is the core feature that justifies the hybrid architecture. It allows the mixing drum speed to be completely decoupled from the engine speed. In fact, it allows the engine to be completely off while the drum is still running.
Which is crucial for those ZEV zones.
Exactly. And the architecture is a series setup for the ePTO itself.
How does that work?
It runs from the HV battery to a dedicated ePTO inverter, which powers a dedicated e-motor. This motor then drives a hydraulic pump, which finally powers the mixer drum's hydraulic motor. It's a fully electrified auxiliary drive system, allowing for very precise control.
And precise control over mixing speed must be vital for different types of concrete mixtures.
It is. The system has to support agitate mode for transport mixing, which is typically 2 to 6 RPM, discharge mode for unloading, and cleaning modes. To do this, the ePTO requires 40 kilowatts of continuous power for agitation and 60 kilowatts of peak power for reversal or high-speed discharge. That's a significant sustained electrical load.
Now we come to the single most high-stakes requirement in the entire blueprint, mandatory triple redundancy for the concrete setting disaster. You used a memorable phrase for this, mending the can.
That phrase really captures the severity of it. If the power system fails and the drum stops for too long, and depending on the mix, it could be as little as 30 minutes in hot weather, the concrete sets inside the drum.
And you can't get it out.
You cannot chip it out. That vehicle is essentially scrap metal. You're talking massive losses in vehicle costs, payload loss, and environmental cleanup. The architecture must be designed to make this failure scenario statistically impossible.
This transforms the engineering into a fail-safe strategy. So what is the first layer of defense?
Redundancy layer 1, fail-safe logic or limp home. The system acknowledges that faults are inevitable, but not all faults are catastrophic. So if the VCU detects a non-fatal fault, like a momentary self-clearing HVL break or minor insulation fault, the system must not immediately cut all high voltage.
Unless it's a major short circuit.
Right, unless a definitive high current short circuit is detected.
So instead of immediate shutdown, what happens?
It enters limp home mode. This limits the main vehicle speed, puts the engine into a reduced power map, but critically, it prioritizes and maintains minimal ePTO function for a limited time, say 30 to 60 minutes.
So the driver can get somewhere safe.
It allows the driver to maintain agitation, drive slowly to the yard, or reach a place where they can safely connect backup power.
That is a direct example of ISO 26262 applied to a specific vocational hazard, prioritizing the drum over all other functions. What about the second layer, if the electrical fault is total?
Redundancy layer 2, hydraulic bypass interface. This addresses the situation where the entire HV system is dead. The battery pack, the inverter, the control units, everything. The ePTO hydraulic system has to include physical quick disconnect couplings, similar to what you see on construction-heavy equipment.
Meaning you can bypass the truck's electrical system entirely.
Precisely. The operator connects an external, portable hydraulic power unit, often called a drum saver or a mend-the-can preventer, to this interface. This external unit then manually drives the drum's hydraulic system for an emergency discharge.
So you save the truck and the load.
You save the truck and the load. It's a low-tech, purely mechanical escape route for an electrical catastrophe.
That blend of high-tech electrification and robust mechanical backup is ingenious. What's the final third layer for a total systemic failure?
Redundancy layer 3. Mechanical engine PTO backup. Even with the P2 hybrid architecture, the source recommends retaining the physical ability to engage a mechanical PTO shaft or gearbox interface as the final backup. If the engine can be started, even if the hybrid components are dead, it has to be able to provide basic, raw power to the drum.
So you're covered no matter what.
This ensures that even if both the hybrid electrical system fails and the external drum saver isn't immediately available, the truck's internal combustion engine can still save the load.
That triple redundancy strategy is the ultimate manifestation of functional safety tailored to the concrete industry. It's a key lesson for any engineer entering this field.
It really is. You have to anticipate the unique, catastrophic failure modes of your specific vocational vehicle and design your architecture around mitigating them, not just maximizing performance.
So moving from these application-specific challenges, let's focus on the universal pillars of high-voltage systems, a core safety mechanisms and communication networks that apply to every EV.
Right. This is pillar the fourth, the safety and communication backbone.
Let's start with the high-voltage interlock loop, or HVIL. We know it has to be a hardwire loop, but what's the mandate for advanced detection?
The mandatory adoption is indeed the hardwire loop because it provides that instantaneous physical fault detection independent of any software or CAN bus message. However, the sophistication lies in the diagnostic coverage. It has to go beyond simple open or closed circuit detection.
Ow.
The source strictly mandates that HVIL monitoring must use a PWM signal, a pulse width modulation signal.
Okay, why mandate a constantly pulsing PWM signal instead of a simple steady voltage check?
Well, a simple DC voltage check can only tell you if the loop is complete or if it's broken. It can't tell you how it broke. By monitoring the returning frequency and duty cycle of a PWM wave, the VCU or BMS acts like a sophisticated sensor. It can precisely distinguish between the three main failure modes: an open loop, a short to ground, or a short to power supply.
So instead of just saying fault, the VCU can diagnose HVIL wire is shorted to the chassis versus HVIL wire is broken completely.
Exactly. That diagnostic coverage is essential for functional safety under ISO 26262. Knowing the precise nature of the fault allows the VCU to execute the appropriate fail-safe action, supporting systems like that limp home mode, which needs to know if the fault is immediately life-threatening or manageable.
Now let's talk about the physical safety of connecting high-voltage components, the connectors themselves.
This is governed by the requirement for last mate, first break mechanical properties. All HV connectors have to be engineered so the HVIL pins are physically shorter than the main power pins.
What's the safety consequence of the HVIL pins being shorter?
When a maintenance technician, or worse, collision trauma, begins to pull a connector apart, the HVIL pin separates before the main power pins physically lose contact.
And breaking the HVI first.
It instantly trips the contactors, cutting the high voltage before the power terminals can pull apart under load and cause a dangerous, massive electrical arc. That's a major fire and safety risk.
And the required response time for that entire process is incredibly strict, right?
Total time from HVIL detection to main contactor cutoff has to be less than 100 milliseconds. This ensures that the system reacts faster than human response time, always prioritizing safety.
Okay, complementing the HVIL is the active discharge mechanism, which addresses the residual voltage in those massive DC link capacitors we talked about.
Yes, the active discharge requirements mandated by ISO 6469-3, this is a crucial legal mandate. After the system is shut down or after a collision, the high voltage bus voltage has to drop below the safe limit of 60 VC within a hard limit of 5 seconds.
That 5-second window seems incredibly fast, considering the size of the capacitors.
It is extremely fast, especially for a large system. It requires a dedicated dual discharge strategy. The primary strategy is the inverter active discharge. The VCU tells the traction motor's inverter to rapidly drain the capacitor's energy into the motor windings by controlling a non-torque producing current.
And that's the fastest way.
It's the fastest method, often achieving the 60 V cutoff in under 1 to 2 seconds.
So the inverter, which is already there, does the heavy lifting most of the time. What about the necessary backup, the redundancy?
The redundant strategy requires an independent, dedicated discharge circuit. Usually it's a resistor bank and a MOSFET switch located inside the PDU. This passive safety mechanism activates if the MCU fails or if the motor circuit is physically cut due to collision, rendering the primary path useless.
It's a failsafe.
It's the fail-safe to guarantee that 5-second deadline is met under virtually any failure mode.
That dual approach ensures compliance and protects rescue personnel. Let's shift to equipotential bonding and grounding, which focuses on electric shock protection via the vehicle body itself.
Equipotential bonding is crucial for personal safety. If the insulation inside an HV component fails, the metal casing becomes energized. Bonding ensures that all conductive outer casings of all HV components are robustly and electrically connected to the chassis. This makes the entire vehicle structure a common electrical reference point.
Which prevents a difference in voltage between parts you can touch.
Exactly. It prevents a potentially lethal difference in voltage between different touchable metal parts.
And what's the specific resistance standard they must meet for this grounding?
Standard is uncompromising. The resistance between any two touchable conductive parts and the electrical chassis must be less than 0.1 ohms or 100 milliamps. This is an R100 standard requirement, and it has to be verified with a testing current of 0.2 amps or greater to ensure that the contact connection is stable and low resistance, even under mechanical stress.
How do engineers guarantee such low resistance in a vehicle that vibrates constantly and gets covered in road grime?
The implementation details matter immensely. The report mandates the use of braided copper strap for connections, not standard single conductor wire.
Why braided?
Braided strap offers superior mechanical flexibility and, critically, superior high-frequency impedance properties, which helps with electromagnetic compatibility. And the mechanical preparation is old school. All grounding points have to be scraped clean of paint and oxidation before attachment. You can't just rely on the bolt threads for connectivity.
That's a great example of a mechanical discipline directly enabling a high-tech electrical safety requirement. Let's look at the grounding topology itself. The HV system uses hybrid grounding. Why?
So, the low-voltage 24V system uses conventional star grounding. The HV system must use hybrid grounding or high-impedance grounding. This means the HV bus is fundamentally insulated from the chassis. It's an IT system, but it is coupled to the chassis via small Y capacitors.
That sounds counterintuitive. Why intentionally couple it with capacitors if the goal is insulation?
It's a necessary engineering trade-off. The insulation, the IT system, prevents DC leakage and electric shock risks at low frequencies. However, the high-frequency switching of the inverters generates massive common mode noise. The Y capacitors are specifically placed to short-circuit and filter this high-frequency noise, preventing it from radiating and causing electromagnetic interference with other vehicle systems.
So it's filtering the AC noise while maintaining the DC insulation for safety.
It's a brilliant way to simultaneously manage safety and electromagnetic noise.
Okay, let's transition to the neural network. The communication network architecture. This heavy-duty application lives on the J1939 standard.
J1939 is the commercial vehicle backbone, but a hybrid system generates an enormous amount of data. So the source mandates a segmented CAN network structure to manage traffic congestion. We have 4 mandatory segments.
Which are?
VCAN for the vehicle and chassis, which means 500 kilobps for real-time control, BCAN for the body and ePTO at 250 kilobps, ICAN for the instrument cluster, and DCAN for diagnosis.
The 500 kilobps speed for VCAN suggests that network needs to be absolutely instantaneous for things like regenerative braking and torque blending.
It does. And speed isn't enough. Capacity management is key. The report institutes strict bus load management rules. The average load has to be below 40%, and the peak load during any 10 millisecond interval must be below 70%, with a strict recommendation to keep it under 60%.
Why such rigid limitations on capacity?
To prevent traffic jams that could delay high-priority messages. In a hybrid system, a delayed message about requested torque or available regeneration current can compromise both safety and performance. The system has to guarantee that critical parameter group numbers, or PGNs, are never dropped or significantly delayed due to congestion.
Which are the most critical PGNs for this truck?
The highest priority message is TSC1, Torque Speed Control 1. This is the VCU sending real-time demands to the traction inverter. Equally high priority is EEC1, which provides immediate feedback on motor status and temperatures. These messages have to maintain strict periodicity regardless of other network traffic.
Now, we noted that ePTO systems often use industrial automation protocols like Canopen. How does the vehicle's J1939 network communicate with those industrial components?
This requires a highly capable central vehicle control unit. or VCU. It has to act as a seamless translator, performing what's called gateway mapping. It translates the industrial CANOPIN protocols, specifically the PDOs, which are periodic status updates, into J1939 PGNs.
What about calibration data?
It also translates the SDOs, which are used for calibration and parameters, into J1939 UDS diagnosis services. And this synchronization delay between the two networks must be less than 20 milliseconds to maintain control stability.
So the VCU is not just the brain controlling the blend of power. It is the simultaneous interpreter ensuring the specialized body equipment and the core chassis systems communicate perfectly. It's the linchpin of integration.
It is the linchpin, ensuring both system function and regulatory compliance.
We focused heavily on the 400V system, but the entire architecture relies on the robustness of the 24V low-voltage system to power controllers and safety relays. What are the key planning elements for the 24V side?
The 24V system is crucial because it acts as the bootstrap. It powers the VCU, the BMS, and the coils for the main high-voltage contactors. The DC-DC converter is the replacement for the traditional alternator, converting 400 VDC to 24 VDC. It has to be rated between 3.0 and 5.0 kilowatts to handle high-load accessories.
Like cooling fans and steering pumps?
Exactly. Large cooling fans, hydraulic steering pumps, lighting arrays.
And since the DC-DC is now managed by the VCU, we can optimize the 24V battery health, right?
Precisely. This enables smart charging. The DC-DC output voltage has to be dynamically regulated by the VCU, typically between 26 and 28.5 volts via the CAN bus. This allows the system to implement the necessary three-stage charging cycle bulk, absorption, and float for the 24V battery, which maximizes its lifespan.
That's critical, since a dead 24V battery means the whole 400V system can't even power up.
Exactly. And then you have to consider when the vehicle is parked for extended periods at the depot.
Right, quiescent current.
That's quiescent current management. The total sleep current for all high-voltage controllers, VCU, BMS inverters, must be suppressed to an absolute minimum, less than 100 microamps total. Any draw higher than that risks completely depleting the 24V battery during long parking periods, leading to a no-start condition.
100 microamps? That is an incredibly low threshold. That mandates highly specialized sleep modes for every single controller.
It does. And furthermore, the VCU has to have a timed wake-up feature. If the VCU monitors the 24V voltage dipping below a critical threshold, it can automatically wake up the DC-DC converter and boost the 24V battery, assuming the HV battery has sufficient charge. It's proactive architectural health management.
Shifting focus now to the overarching process, Pillar V is all about the V-model development logic. This is the structure that ensures the entire effort adheres to the consultancy's goal, building development capability.
The V model is the systematic approach to manage the complexity and risk introduced by electrification. It ensures that development is systematic and that every design decision is verified against its initial requirement. This is how you transition from that reactive diesel thinking to structured electrical system engineering.
Okay, so the left side of the V is the definition phase. How does the report mandate this phase be executed for heavy-duty trucks?
It starts at the absolute top with the Vehicle Technical Specification, or VTS. A non-negotiable top-level requirement such as the 32-ton truck must achieve a 30% grade start from zero.
And from there, you work backwards.
From that VTS, engineering must work backward. You calculate the required wheel torque, then backward calculate the necessary motor torque and speed, and finally you define the required peak and continuous DC power draw from the battery.
That systematic backward calculation then dictates the statement of requirement, or SOR, that goes out to suppliers for components.
And the SRR is the crucial technical deliverable. It has to be exhaustive. It must include precise voltage and current ranges, peak and continuous power specs, detailed thermal management requirements, and the specific ASIL targets, like ASIL D for the BMS.
What else?
Critically, it must mandate the submission of efficiency maps detailing efficiency across the entire operational range, not just a single peak number. The report requires mapping efficiency at a minimum of 3 distinct operating points.
That ensures you aren't buying a component that looks great on paper but falls apart under real-world continuous load. And the right side of the V is validation, proving that everything meets those initial requirements.
Correct. The right side is rigorous testing. Component testing validates the SOR specifications. System testing verifies the functional and safety interaction between components, like HVIL function and discharge time. And finally, vehicle validation confirms the entire assembly meets the initial VTS.
Does it actually start on a 30% grade?
Exactly. Everything has to be traced back to the mandatory regulatory compliance matrix.
Let's quickly review that final matrix, the non-negotiables that the final product must satisfy to be legally sold and operated.
The list is absolute and multi-jurisdictional. You've got ISO 26262 for functional safety, requiring a full hazard analysis and risk assessment, ISO 64693 for electrical safety, covering insulation and contact protection, ECE R100.03, the core EU certification standard, and then GB 18384 2020, the Chinese mandatory standard.
And that one has a very specific requirement, doesn't it?
It does. It requires the extremely specific feature of a 5-minute thermal runaway pre-alarm.
5 minutes. That gives the operator a window to move the vehicle before a catastrophic thermal event. That level of detail across these 5 pillars, from the P2 topology to the PWM-driven HVIL, demonstrates a true transition in engineering mindset.
It's a complete roadmap for systemic risk management.
So to wrap this all up then,
This entire blueprint, laid out in this detailed specification, clarifies the core value of systems engineering. It's the strategic document that enables a team to move from diesel thinking, where auxiliary systems were often secondary, to electrical system engineering, where safety, redundancy, and power integrity are centrally managed from day one.
it's not about what parts you buy. It's about the sophisticated architecture that connects them and the rigorous V-model process that verifies them against the strictest safety and performance standards.
Right. And the key takeaway for you, the learner, is this. The successful electrification of heavy-duty vocational vehicles hinges entirely on anticipating those unique catastrophic failure modes, like the concrete setting disaster, and embedding multi-layered safety and operational redundancy from the start.
That means the PWM monitoring for diagnostics, the dual active discharge for physical safety.
And the triple ePTO backup for operational continuity. Avoiding expensive, reputation-damaging rework starts with perfect architecture and process discipline on day one.
And that leads us to a final provocative thought. Looking beyond this advanced hybrid system, the source explicitly notes that this 400V P2 hybrid platform, by building organizational expertise in high-voltage component integration and system safety, lays a solid, scalable foundation.
It does.
So if this system successfully transitions engineering teams to high-voltage expertise, what does the necessary next step look like?
Well, if the 400V P2 hybrid platform proves the ePTO redundancy and system reliability in the harshest conditions, the next logical engineering project is the full elimination of the combustion engine.
A fully electric mixer.
Right. That means transitioning this standardized 400V architecture, including the high-capacity PDU and cooling systems, to a high-energy density, pure electric heavy truck platform. Or perhaps integrating a different power source entirely, like a large-scale hydrogen fuel cell system, which would require the exact same high-voltage distribution expertise built during this hybrid project.
The blueprint is built for today's regulation, but with an eye toward tomorrow's inevitable transition. A truly fascinating look at the future of construction logistics and heavy-duty engineering. Thank you for joining us for this deep dive into the high-voltage architecture of the hybrid cement mixer truck.
Always a pleasure.
We'll get you next time for the next deep dive.